All right, next, my second story is of another galaxy cluster. This is the Perseus Cluster, and this is another really rich galaxy cluster. And don't ask me how far away it is because I forgot that number. So here is yet another really rich field, and in galaxy clusters like this, where you have hundreds or thousands of galaxies all gravitationally bound, there's usually one galaxy that sits right at the center of the cluster, and it's usually the most massive galaxy, and over time, galaxies swallow up other galaxies via mergers. And so the one galaxy that sits at the center of Perseus is NGC 1275, which is right here. And it's been imaged lots of times over the years. Here is an image taken from the Wind Telescope, which is at Kitt Peak outside of Tucson, Arizona. And what they're looking at is light from being emitted by hydrogen atoms. And you can see this weird sort of spider-like, almost explosion of gas originating from the center of this galaxy. And there are also these dark clouds. So these are dust clouds, giant molecular clouds. The Hubble Space Telescope was also used to image the galaxy. So I've basically positioned it. And this is taken with the WithPic 2 camera, which has this weird kind of B-2 bomber shape. So there's more to it, obviously, but the astronomers who one time on Hubble, they only managed to get this much, but you can see that Hubble is able to get more detail. And you can see evidence of, well, this light is probably from stars, but the gas structure, the dark cold gas, is a lot more chaotic looking. And then here is a much more recent Hubble Space Telescope composite image, where they're looking again at the hydrogen gas emission. That's the red, but they're also looking at the starlight. So that's the blue. And like I said earlier, blue starlight indicates that you're looking at relatively younger, more massive stars. There's hints of yellowish and orange or reddish tinted starlight as well, and that indicates more lower mass, older stars. And then Perseus is closer to the galactic plane of our galaxy, so you do see more stars that are contamination. They're basically foreground stars in our own galaxy. And what astronomers think has happened is that NGC 1275 basically merged with another galaxy, a relatively large galaxy, in the recent past, meaning in the last billion years or so. And this merger resulted in gas and stars being pulled out in large these tidal arms, and the stars, the molecular clouds also got compressed, and they probably led to a new wave of star formation. And the star formation resulted in lots of gas being expelled from the winds and the supernova explosions from these massive stars. And so that's why you have these giant streamers of gas. Now, what's interesting is that if you look at this cluster in X-rays, and this is using the Chandra Space Telescope, you see, and the galaxy is down here in the middle somewhere, but the X-ray gas is much, much larger than the galaxy. And it turns out that these very rich clusters with lots of galaxies in them, most of the mass in these clusters are not located inside the galaxies, but they're inside, they make up the gas that fills the space in between the galaxies. So there is gas that's tens of millions of degrees Celsius, and they emit only in X-rays because they're so hot. And this gas is likely to have been expelled by the galaxies, either by supernovas or stellar winds, and even by the black hole engines inside the centers of these galaxies. And so the Chandra X-ray Observatory is excellent for studying this gas. And in this case, the paper that I'll be talking about deals with this second image, this redder image, and you're seeing all of this emission from the X-ray gas that's centered around 1275, NGC 1275. This other image here is an earlier Chandra image where they're trying to get more detail in the region immediately close to the galaxy, but this new research is looking at this entire region almost, at least 500,000 light years across. If you look at this bar, probably close to 3/4 of a million light years across, that's being filled by this X-ray emitting extremely hot gas. And what the authors of this paper notice is there seems to be this what they call a bay, meaning there seems to be a lot of X-ray emitting gas that's sort of concave around the central galaxy, but there's this one part that's convex. It's turned around, and it doesn't seem to match the features of the other X-ray emission. And so they puzzled as to why this feature is in there. And their interpretation is that this might be something known as a Kelvin-Helmholtz instability. And this is something that comes out of the study of fluid dynamics, and this is something that you've probably seen in clouds above Colorado or anywhere on the horizon. So here is a tweet from Breckenridge Resort from a couple year and a half ago, where they talked about they're about to open, but here are some nice clouds with this Kelvin-Helmholtz instability, where you see these waves appearing in the clouds. This also appears in clouds that are banded, and I'm sure many of you have seen clouds like this in our skies. This kind of rolling pattern is another, is when you're seeing these instabilities from below. And then here is another really brilliant example of it over the Flatirons in Boulder, where you're seeing these clouds. And the way that these instabilities form is when you have a colder air mass below a warmer air mass, and the two are moving at slightly different speeds, and the shearing effect creates this turbulence. And so these cells are basically turbulent cells, and depending on where the moisture gets cut off in the cloud, you can get these really nice looking wave-like patterns. But it has, in order for this instability to occur, you have to have a temperature difference, meaning part of it has to be warmer, the other part has to be colder, and there has to be a velocity difference between the two. Well, in this particular paper by an astronomer, led by an astronomer named Scott Walker, they are positing that we're seeing this Kelvin-Helmholtz instability in the X-ray emitting gas in the Perseus cluster. And what they do is not only have they looked at the Perseus cluster, but they've looked at two other clusters. So here's Abell 1795. It's one of these Abell clusters that I talked about right at the start. And in addition to the X-ray gas, so this is from the Chandra X-ray telescope, they also looked at these clusters in radio. And it turns out this X-ray, this extremely hot gas, emits a lot in X-rays, but it turns out that the electrons in the gas can also emit in radio waves. And so these contours are from a radio telescope, in this case the VLA, and you can see it plotted on top of the X-ray emission. But what's really interesting is that dark bay that we saw in Perseus, you also see it in Abell 1795, but there's a deficit of emission in the radio. So that means that there doesn't seem to be any hot gas right there. So it's not just, there's definitely something that's different about this bay compared to other regions of the cluster. Here's the Centaurus Galaxy Cluster, and again they see this kind of this indentation, this convex region, And again, there's a shortage of radio emission. And then finally, whoops, I think I'm going in the wrong direction. Oh. And so what they do is they run simulations of what could result in this bay, and they're able to actually reproduce. So this is the observation. Let's go back to here from Chandra, and this is the computer simulation. And the simulation was able to reproduce what they think is a Kelvin-Helmholtz instability. And in addition to the raw Chandra data, the image, they also processed it to bring out, to increase the contrast. And so in this case, it's the same data, but it's gone through this extra level of processing. And so that's why you have all these nice, almost scalloped, overlapping scalloped regions. And again, you see the bay. And at kind of this higher resolution, where they simulate this processing, you again see that bay. And it even vaguely looks like the Kelvin-Helmholtz instability that we saw in the photographs in the Earth's atmosphere. And so how does this work? Well, and then here is the Centaurus cluster, and they run simulations again to bring out the bay, and they changed the magnetic field properties, and they were able to show that if you have different magnetic field properties, you can either increase the size of the bay, or the bay might not show up at all. And so the existence of this can actually lead you to some information about the magnetic properties of the gas. And so here is the simulation. And basically what they do is, in order, they start out with this gas and a passing galaxy that causes a sort of a disturbance, sort of almost like if you threw a rock or a pebble into a pond, and this disturbance propagates in spiral waves. So here we are, we're going to look at it again, and in about 1 billion years, or a couple billion years, you have that disturbance caused by the passing galaxy, and it creates these waves. And it turns out that the inner gas close in to the galaxy is colder than the outer gas, and so here, that's where you get the temperature difference. And so here we are again, and the temperature difference plus the velocity difference will result in the Kelvin-Helmholtz instability. So here it is right there. And then they just let the simulation run. So this instability doesn't, it's somewhat transient. It doesn't stay there forever. So here it is again with the actual Chandra data. And here the video just shows the X-ray gas superimposed on that image that we saw earlier of this particular cluster. So you can see the gas fills a pretty large portion of this particular cluster.